Hello, Accelerated Chemistry students. This is Ms. Crisafulli, and this is your Chapter 4, Section 3 video notes all over distinguishing among atoms. So let's first by starting to talk about Henry Moseley. Henry Moseley was around from 1887 to 1915, and he was a colleague of Rutherford. He found that every element had a unique charge in its nucleus, and he determined that the number of protons in an atom identifies it as an atom of a particular element. So he's the one that's given the idea that the atomic number is equal to the number of protons. So in a neutral atom, that means that the number of protons are going to equal to the number of electrons, because if the atom is neutral or has no charge, then the number of positive particles in the atom are going to be equivalent to the number of negative particles that you have in the element. So let's talk about a problem, problem 4.1, where we're going to look at atomic numbers. So the element of nitrogen has atomic number of 7. So how many protons and electrons are in the neutral atom of nitrogen? So if we were to look at this, we would think about the fact about where nitrogen is on the periodic table, and then we would know that the number of protons are going to be equal to the number of electrons because the atom is neutral. So this is what your nitrogen box on your periodic table looks like. 7's on the top, 14.01 is on the bottom. And so if we were to look at this, we can identify what the atomic number is. And the atomic number is going to be what we're going to use to find the number of protons, and then after that, the number of electrons. So in nitrogen's case, nitrogen has an atomic number of 7. So that means that it has both 7 protons and 7 electrons. Now, if we were to look at a different number that we can determine off the periodic table, we can look at the mass number. So Dalton stated that all atoms of an element are identical, but since then it has been found that some atoms in the same element have different masses. So what particles make up the mass of an atom? Well, that would be the protons and the neutrons. So remember, the mass of the electron is negligible, and we talked about that in our last set of notes. The mass of the proton is 1, and the mass of a neutron is 1 as well. The mass of an electron is 1 over 18,000 and change, and so that's not going to give the mass of an atom much, because it's going to be a very, 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 very small number. So if we know the mass number, we can then calculate either the neutrons, or if we know the protons and the neutrons, we can calculate the mass number. So here are your two equations that you need to be able to know. So mass number is going to be equal to the number of protons plus the number of neutrons, and the number of neutrons is going to be equal to the mass number minus the atomic number. So let's look at another example. So let's determine the composition of these atoms. So how many protons, electrons, and neutrons are in each of the following? Beryllium with a mass of 9 and an atomic number of 4, neon with a mass of 20 and an atomic number of 10, and sodium with a mass of 23 and an atomic number of 11. So let's look at each one of these pieces. So first, we know what our knowns are and our unknowns are. So we know that beryllium has an atomic number of 4 and a mass of 9. We know that neon has an atomic number of 10 and a mass of 20. We know that sodium has an atomic number of 11 and a mass of 23. So what we don't know, though, is how many protons, neutrons, and electrons are in these 3 elements. So let's look at this a little more further. So when we were looking at this, we can use the atomic number to find the number of protons. So we know that the atomic number is equal to the number of protons. So the atomic number of beryllium is 4, so that means that it has 4 protons. We know that the atomic number of neon is 10, so that means that it has 10 protons. And we also know that the atomic number of sodium is 11, so that means that we have 11 protons. Now, if we're moving forward and we're going to talk about electrons, we know the atomic number is equal to the number of electrons when the atom is neutral. All of these elements are neutral, so their atoms are going to have the same number of protons and electrons. So for beryllium, if it has an atomic number of 4, that means it also has 4 electrons. And for neon, if it has an atomic number of 10, that also means that it has 10 electrons. And for sodium, if it has an atomic number of 11, that means that it also will have 11 electrons. Now, remember, electrons are going to be equal to the atomic number when the atom is neutral. If the atom is not neutral, and we're going to talk about that in future lessons, then that is not the case. So let's continue and let's solve for our number of neutrons, which we're going to use the mass number and the atomic number. Remember, the number of neutrons is equivalent to the mass number minus the atomic number. So when we look at these, beryllium had a mass of 9, so that means that we take 9 minus 4, and that will give us 5 neutrons. Neon had a mass of 20, and if we subtract the 10 protons from that, that means that we'll have 10 neutrons. And sodium has a mass of 23, so if we subtract the 11 protons from it, that means that we have 12 neutrons. So then we have to evaluate. Remember, that's the last step when we're doing mathematical problems. Does it make sense? And it makes sense because the mass number is equal to the protons plus the number of neutrons, and the atomic number is equal to the number of protons and electrons because these atoms are neutral. So now let's talk about something else that we can talk about when we consider atoms, and we can talk about isotopes. And look at these 3 pictures of neon. How are they different? Well, it says neon 20, neon 21, and neon 22. They each have 10 protons. They each have 10 electrons. But wait, their neutrons are changing. Why is that? And that is because isotopes are atoms that have the same number of protons but a different number of neutrons. So neon 20, 21, and 22 are the 3 isotopes of neon, and the only difference that they have is that they have a different number of neutrons, which will give them a different mass number. So when we're talking about isotopes, we have isotopes of an element that have different number of neutrons, so they have different mass numbers. They're chemically alike because they have the same number of protons and electrons. And the number of neutrons in an isotope does not change which element it is because the atomic number does not change. The atomic number stays the same when it's an isotope. So let's look at how to write different isotopes. So we're talking about 2 stable isotopes of carbon, which are carbon-12 and carbon-13. So we're going to write the 2 isotopic notations for these 2 isotopes of carbon. So the first thing we need to do is we need to know how many, what the atomic number is and what the mass number is. And so then first we're going to look at the periodic table for carbon. So here is the box for carbon on your periodic table. The symbol for carbon is C, so we're going to need that to write our symbol. And the atomic number is 6, so we're also going to need that. And the last piece of information that we're going to need is the mass number. Now, the mass number is given to us because if we look, for example, carbon-12, the mass number is 12. And when we look for carbon-13, the mass number is carbon-13. So you can look at the name of the isotope in order to determine what the mass number is. So when we look at this and we're going to actually write our symbols, it's super easy. We need to make sure that the mass number is in the top left-hand corner of the symbol and the atomic number is in the bottom left-hand corner of the symbol. So let's look at carbon-12. So the C is going to go here. Top left-hand corner, we're going to put a 12. Bottom left-hand corner, we're going to put a 6. And the same thing for carbon-13. We're going to use a C for our carbon. And we're going to use 13 for the mass number, which goes in the top left. And we're going to use 6, which is the atomic number, goes in the bottom left. Now, if you look at these 2, they look very similar, but the only thing that is different is their mass numbers. And that means that the carbon-13 has 1 more neutron in its nucleus than it does when it is carbon-12. And now the final thing that we can talk about in this section of our textbook is we can talk about atomic mass. Now, we know that the number of protons plus the neutrons contributes to the mass of the atom. And we know that when you look at the periodic table, the atomic mass is not a whole number. And that doesn't make sense because the protons and the neutrons are whole atoms or in whole subatomic particles. So you can't have part of a proton or part of a neutron. So what does that mean? This leads us to what we know as atomic mass. Atomic mass is when we take into account the masses of each isotope. So each element that has a decimal point for its mass on the periodic table has at least 2 naturally occurring isotopes. And so the atomic mass of an element is a weighted average of the mass of the atoms in a naturally occurring sample of the element. So the weighted average mass reflects both the mass and the relative abundance of the isotopes as they occur in nature. So when we think about this, magnesium 12 does have three isotopes, one with a mass of 24, one with a mass of 25, and one with a mass of 26. And the relative abundance is how often they will exist in nature. And so the atomic mass takes that into account. So it is a weighted average. So when we write atomic mass out, we have to have units with them because they are numbers. And so we use the atomic mass unit, or AMU, and it's based on the mass of carbon-12. It's approximately 1/12 the mass of carbon-12. And so anytime you see us writing atomic masses, we're going to be writing them with units of AMU. So let's look at a sample problem, sample 4.4, and we can understand how these relative abundance work if we look at the two isotopes of copper, copper 63 and copper 65. The atomic mass of copper is 63.546. So if we were to look at that and really understand the fact that we know that the atomic mass of an element is a weighted average of the atoms in a naturally occurring sample of the element. So if we were to look at this and analyze it and solve this question, we can compare the atomic mass to the mass of each isotope. So the atomic mass of 63.546 is closer to 63 than it is to 65. So that means that the average atomic mass is going to be closest to the most abundant isotope. So, and that will make sense because the most abundant isotope is going to take up most of the mass of the element. Now, we can also calculate the atomic mass. We can calculate the atomic mass because we can know three things about an atom. So we can know the number of stable isotopes for that element, we can know the mass of each isotope, and we can also know the percent abundance of each isotope. So if we know these things, then we can calculate the atomic mass of the element by simply multiplying the mass of each isotope by its natural abundance expressed as a decimal. Then we're going to add all those values together. So this would be your equation that you need to know. Now this could be different because some elements will have two isotopes, some will have more. So you basically will do the mass of each isotope times the abundance of that isotope in a decimal form, and then we're going to add them together as we continue on. So let's look at an example problem of this and look at what this looks like. So if we were to look at element X, it has two naturally occurring isotopes, one with a mass of 10.012 AMU, and that happens 19.91% of the time, and one with a mass of 11.009 AMU, and that happens 80.09% of the time. And we're going to calculate the atomic mass of this element. So to do this, we're first going to list, this is a math problem, remember, we're going to list our knowns and unknowns. So here's all the information that we know. And I already went and calculated the percents and changed them to decimals, so that will make it easier. And the one thing we don't know is the atomic mass of this element X. So to start solving it, we're going to calculate the masses that is contributed from each isotope. So for the X isotope with a mass of 10, if we were to take the average mass of that isotope times it by its percent, we'd get 1.993 AMU. And we could do the same thing for X. We'll take the mass of the isotope, 11.009 AMU, and multiply that by its percent as a decimal form, and we get 8.817 AMU. Final step for this problem is just to add those two values together. The mass of element X with a mass of 10 and the mass of element X with a mass of Y. So here we go. And then our final answer is going to be 10.810 AMU. Well, that's the end of this video. And remember, before we can continue, we got to make sure that this makes sense. And it does, because the most abundant isotope is going to have a value that is closest. So enjoy the rest of your evening. Thank you for watching, and everything from this video has been acquired and adapted from pearsonchem.com and its textbooks, CDs, and resources. Have a good night.